So one characteristic in which most systems differs from application software, the system software differs from application software, is the machine dependency. Okay, application software programmers need not be concerned about the intricacies of the machine instructions and so on and so forth, right? So that transparency is achieved via this systems program. Okay, so an application program is primarily concerned with the solution of some problem using the computer as a tool. The focus is on the application, not on the computing system. System programs, on the other hand, are intended to support operation and use of computer itself rather than any particular application. For this reason, they are usually related to the architecture of the machine on which they are to run. For example, assemblers translate mnemonic instructions into machine code. The instruction formats, addressing modes, etc. are of direct concern in assembler design. Okay. Similarly, compilers must generate machine language code, taking into account such hardware characteristics as the number and type of registers and the machine instructions available. Operating systems are directly concerned with the management of nearly all of the resources of a computing system. So many other examples of machine dependencies may be found throughout this book. So as you see, assemblers, linking loaders, compilers, operating systems, these are all system softwares. Okay. Now, uh, so on the other hand, there are some aspects. So there are two aspects of this system software. One is machine dependent, another is machine independent. We'll study both of them. On the other hand, there are some aspects of the system software that do not directly depend upon the type of computing system being supported. For example, the general design and logic of an assembler is basically the same on most computers. Okay. Some of the code optimization techniques used by compilers are independent of the target machine. Okay. So there is a machine independent code optimization. There may be machine dependent code optimization. Okay. So likewise, the process of linking together independently assembling programs does not usually depend on the computer being used. Okay. So we will also see many examples of such machine independent features, okay, of this system software. Okay. So like for the design of assembler means, but most of the system software is machine dependent. Okay. We must include real machines and real pieces of software in our study. However, most real computers have certain characteristics that are unusual or even unique. It can be difficult to distinguish those features of the software that are truly fundamental and those that depend solely on idiosyncrasies of a particular machine. To avoid this problem, we present a fundamental function of each piece of software through discussion of simplified instructional computer, SIC. Okay. So SIC is a hypothetical computer that has been carefully designed to include the hardware features most often found on real machines, while avoiding the unusual or irrelevant complications. Okay, so in this way, the central concept of a piece of system software can be clearly separated from implementation details with a particular machine. The approach provides reader with a starting point from which to begin the design of a system software for a unfamiliar new or unfamiliar computer. Okay, so each major chapter in the text first introduces the basic functions of the type of system software being discussed. We then consider the machine dependent and then machine independent extensions to these functions. Examples of implementations on actual machines, specifically the major chapters are divided in the following sections. Features that are fundamental that should be found in any example of this type of software. Features whose presence and character are closely related to the machine architecture. Okay. Other features that are commonly found in implementation of this type of software that are relatively machine independent. Okay. major design options for structuring a particular piece of software, for example, single pass versus multi-pass, okay, processing, okay. So these are some paradigms, okay, that are used in designing this system software, okay. In assembler also you'll see that single pass, one pass assembler, two pass assembler. First we discuss two pass, that is simpler to design, and then we go for one pass, okay. So examples of implementations of actual machines stressing unusual software features and those that are related to machine characteristics. So now we'll describe this simplified instructional computer, the architecture, and the corresponding assembly language. Okay. So in this section, we describe the architecture of our simplified instructional computer, SIC. This machine has been designed to illustrate the most commonly encountered hardware features and concepts while avoiding most of the idiosyncrasies that are found in real machines. Like many other products, SIC come in two versions, the standard model and XC. XC stands for extra equipment or perhaps extra expensive. The two versions have been designed to be upward compatible. Okay, that is, an object program for the SIC machine will also execute properly on the SIC XC system. Since the upward compatibility is often found on real computers that are closely related to one another. Okay, so now we'll discuss this SIC. And then we'll present the features that are present in SIC XC programming. Okay, so these there are examples that are intended to help you to become more familiar with SIC and SIC XC instruction sets and assembly language. Okay, so we'll see this. First, we'll see the machine architecture, instruction set, and some assembly language programs on both SIC and SIC XC machines. Okay, so SIC, first we'll discuss the SIC architecture, the simplified instruction set computer. So it has a memory which consists of 8-bit bytes, 3 consecutive bytes, that is 24 bits, form a word. All addresses on SIC are byte addresses. Words are addressed by the location of the lowest numbered byte. Okay, there are 2 to the power 15, that is 32,768 bytes in the computer memory. Okay, so the address field is 15 bits. Okay, so you can see the registers. So there are in the SIC machines, there are only 5 registers, and this numbering is done in such a way that like you can see 3, 4, 5, 6. These are vacant slots. Actually, in SIC XC, we will assign registers with those numbers. That's why this numbering has been done in this way. Okay, so there are 5 registers, all of which have special uses. Each register is 24-bit in length. The following table indicates the numbers, mnemonics, and uses of these registers. The numbering scheme has been chosen for compatibility with XC version of SIC. So mnemonic for the register A, and the corresponding number is 0. A stands for accumulator for arithmetic operation. X, the number is 1. It stands for index register used for addressing. L, the corresponding number is 2. It stands for linkage register. This is used for jump to subroutine instruction that stores the return address in this register. PC stands for program counter. Its number is 8. Program counter contains the address of the next instruction to be fetched for execution. And SW is the status word. So status word contains a variety of information, including the condition code. Okay. So now we'll see the data formats. So integers are stored as 24-bit binary numbers. Okay. In 2's complement representation is used for negative values. Characters are stored using their 8-bit ASCII codes, and there are no floating point hardware on the standard version of SIC. In SIC XC, it is there. Okay. So all machine instructions on standard version of SIC have the following 24-bit format. Okay. So this is the first 8-bit is the opcode. Okay. Then X stands for the flag bit, which is used for deciding on the addressing mode. Okay, and then we have the 15-bit address field. Okay, so there are two addressing modes, as you can see. There are available, indicated by setting the X bit in the instruction. The following table describes how the target address is calculated from the address given in the instruction. Okay, so parentheses are used to indicate the contents of a register or memory location. For example, parenthesis X represents the contents of the register X. Okay, so if X is set to 0, the addressing mode is direct addressing mode. Okay, and this address in this 15-bit field, this is TA. TA stands for the target address. Okay, so target address is stored in this 15-bit field when X is 0. When X is 1, the addressing mode is indexed. Okay, so in that case, target address is calculated adding, this is sort of the so this is the index, so that is added with the content of the index register, that is X. Okay, so the content of the index register is added with this content, with this value that is stored in the address field to obtain the actual target address. Okay, so suppose you have LDA 10. Okay, so this is the opcode. Okay, LD, this is the opcode. So now just a minute.
हेलो हाँ हाँ मैंने तो 8:30 बोला था ठीक है तो मैं रेडी हो रहा हूँ तो तुम वेट करना मैं अभी वहाँ आता हूँ ठीक है
ओके
ठीक
so the effective address is 1000. Okay, that is stored in this address field 10. Okay, so the content of 1000, okay, LDA is load accumulator. Okay, so the content of this memory location, okay, is stored in the accumulator. Okay, so this is the direct addressing mode, and we have the indexed addressing mode. Okay, so the indexed addressing mode is illustrated here. Okay, suppose STCH, that is store character. Okay, buffer X. Okay, so this is buffer is this 15-bit field. The content of this buffer is added to the content of X. So effective address is calculated adding this content is 10000. This is in so this is this is this number is actually in hex, so it is this content is added to the content of X. So this gives the effective address, and the content of that location, of that effective address, in that place the accumulator content will be transferred. So the accumulator content, the character is loaded into the effective address. Okay, so these are two addressing modes that are available in SIC. That is a much simplified version. SIC will have lot more rich addressing modes. In SIC, simple addressing modes, for which I have given you to design the assembler because your life will be simpler. Okay, so instruction set. Okay, so SIC provides a basic set of instructions that are sufficient for most simple tasks. This includes the load registers, load and store registers. Okay, so load accumulator, LD is load accumulator, LDX is load index register, ST is store accumulator, STX is store index register, etc. Okay, so these are load and store registers, as well as Integer arithmetic operations like add, sub, mul, div, addition, subtraction, multiplication, division. All arithmetic operations involve register and a word in memory, with the result being left in the register. Okay, there is an instruction comp that compares the value of register A with a word in memory. The instruction set sets a condition code, okay, CC, to indicate the result less than, equal to, or greater than. Conditional jump instructions like JLT, JEQ. JLT is jump less than, JEQ is jump equal to, JGT is jump greater than, can test the setting of condition code. Okay, CC stands for this condition code, and jump accordingly. Two instructions are provided for subroutine linkage. JSub, that is jump to subroutine, jumps to the subroutine, placing the return address in the linkage register L, and RSub returns by jumping to the address contained in the linkage register L. Okay, so we'll see now the how the input output is performed in SIC machine. On the standard version of SIC, input and output are performed by transferring 1 byte at a time to and from the rightmost 8 bits of register A. Okay, so each device is assigned a unique 8-bit code. There are 3 IO instructions, each of which specifies the device code as an operand. Okay, so that the one instruction is test device. It does a polling operation on the IO device. Okay, TD, okay, instruction sets whether the address device is ready to send or receive byte of data. Okay, so the condition code is set to indicate the result of this test. Okay, a setting of less than means the device is ready to send or receive, and equal means the device is not ready. So a polling is done based on this condition code. When the device is ready, the data gets transferred. Okay, so so a program reading to transfer data must wait until the device is ready, then execute read data or write data instruction. The sequence must be repeated for each byte of data to be read or written. Okay, so we'll see some program that performs this input-output operation also. Okay, so this is the instruction set for the simplified instructional computer. Then we'll move over to the SIC XC machine architecture, the extended version. Okay, so that you have to use in designing of this linking loader. So I have to cover this topic also. Okay, because it will be the assembler we will be designing will be you have to just little bit modify. Okay, that assembler will be required in conjunction with the while you are designing the linking loader, the code you have written for the assembler, you will have to use that code. Okay, and that you have to modify a little. Okay, with this SIC machine architecture. Okay, so the memory structure for SIC is same as that previously described for SIC. However, the maximum memory available on SIC system is 1 megabyte, that is 2 to the power 20 bytes. Okay, the increase leads to a change in instruction formats and addressing modes. Okay, so it's earlier you have seen that they have 2 to the power 15 bytes of memory. Now we have 1 megabyte of memory in SIC machine, so 20-bit address. Okay, so the registers, as I told, we have already 5 registers earlier. They are also there in SIC machine. Additionally, okay, so the following additional registers are provided in SIC machine. So B stands for the base register, whose number is 3. This is used for addressing. S is a general working register. This does not have special use. Its number is 4. T is another general working register. No special use. Number is 5. F is the floating point accumulator. Here floating point arithmetic is supported and its number is 6. Okay, and the data format that is used in the SIC version So SICXC provides the same data formats as the standard version. Okay. So in addition, there are 48-bit floating point data type with the following format. S stands for sign bit, then you have exponent, then the fraction. So, or the mantissa part, okay, of the floating point number. So the fraction is interpreted as a value between 0 and 1 that is assumed to be a binary point immediately before the higher order bit. Okay, so it is normalized floating point representation. For normalized floating point numbers, the higher order bit of the fraction must be 1. The exponent is interpreted as an unsigned binary number between 0 and 2047. Okay, and this is actually, you will see that this 11-bit exponent, so 2 to the power 11 is 2048, so it is ranging from 0 to 2047. So 2048 exponents are possible actually that way. So the exponent value E and the fractional value F and the absolute value of the number is represented by F times 2 to the power E. Okay. So this is so the sign of the floating point number is indicated. Okay. Indicated in indicated by the sign bit. Okay, which is 0 for positive and 1 for negative. A value of 0 is represented by setting all bits, including sign, exponent, and fraction to 0. Okay. So instruction formats. Now we'll see the instruction formats. So the larger memory available in SICXC machines, it has a more rich, it has more addressing modes actually. So the larger memory available on SICXC machines that address will in general no longer fit in 15-bit field. Okay. So because it is a 20-bit address field. Okay. So thus the instruction format used uh, uh, used on standard version of SIC is no longer suitable. There are two possible options: either use some form of relative addressing or extend the address field to 20 bits. Both of these options are included in SICXC machines in format 3 and 4. Okay, so we have seen in SIC there are only two addressing modes: direct and this is for x is equal to 0, direct and indexed. Okay. Now you'll see this SICXC. This has that is format 1 and format 2. We have 4 types of formats in the addressing modes. Okay. So in addition, SICXC provides some instructions that do not reference memory at all. Okay. So these are like immediate addressing mode. Okay. So formats 1 and 2 in the following descriptions are used for such instructions. Okay, the new set of instructions is as follows. The setting of the flag bits in formats 3 and 4 are discussed under addressing modes. Bit B is used to distinguish between formats 3 and 4. Okay, so E is equal to 0 means format 3. So that is, and E is equal to 1 means format 4. That is the extended version. You will see in the jump to subroutine, in many cases, there is a plus symbol before that instruction that is extended. For that, this E bit will be set to 1. Okay, so appendix A indicates the format to be used with each machine instruction. When E is equal to 1, the address field is set to 20 bits actually. So this that is used in format 4 actually. So format 1 is 1 byte. Okay, so here it is a simple example is R sub. Okay, it only consists of the opcode. Okay, so return to subroutine. Okay, so this is format 1 instruction. Okay, so there is no operand field. Okay, and so this format 2 Format 2 has 8-bit opcode. It's 2 bytes. Format 1 is 1 byte. Format 2 is 2 bytes, followed by 2 4-bit fields containing the number of the corresponding registers. Okay, because you have 9 registers, 4-bit would suffice, right? Actually, so that these 4 bits indicate the register number. So compare AS. Okay, so if you have this instruction, okay, so this is stored in S is the so number corresponding number A is I think 0. That's why it is not stored, and S is actually this is 4, right? So you can see, check in the previous page, the number for S is I think 4. Yeah, S is 4, right? Actually, that's why 100. Okay, so compare is, so this is the instruction, this is the opcode. Okay, this is the number, the 0 for A and 4 for S. Okay, so this compares the content of these 2 registers. In format 3, we have 6-bit opcode followed by 6 flag bits. Okay, so N for indirect, I for immediate, X for indexed, B for base relative, P for program counter relative, E for this extended format where the address field will be extended to 20 bits. Okay, so these are the flag bits followed by the 12-bit displacement field. Okay, so this is now this is an immediate example of immediate addressing where you see this I bit is set to 1. So load accumulator number 3. Okay, so here in this 12-bit field, the number that is stored that will be transferred into accumulator. So no memory reference is required. It is an immediate addressing. Okay, so I bit is set to 1. And format 4, as I told, okay, here this extended bit would be set to 1. Okay, so and usually N and I are set to 1 in format 4 instructions. Okay, so this uses 20-bit address field. Okay, so this is this you can see 20 plus 6 plus 6, 32-bit instruction. Okay, so and this is plus, there is a symbol plus J sub R direct. So jump to the address 1036. Here directly the address is stored. Okay, so this store address, okay, will be stored in the linkage register actually when this jump to subroutine instruction will be executed. Okay, so the addressing modes, okay, so 2 new relative addressing modes are available for use with instructions assembled using format 3. Okay, so they are described by this table. So one is base relative. When it is base relative, B is set to 1, P is set to 0. And the target address is calculated as adding the content of the base register with the displacement field. Okay, and program counter relative. When it is program counter relative, the address is this B is set to 0, P is set to 1, T is set to content of the program counter plus displacement field. Okay, so what is the address of the relative addressing is basically means if you use this direct addressing, okay, that is directly reference a memory location, then it may so happen that while you are loading the program, you may load it in a different location, and that memory reference may not be legal. Okay, so otherwise you have to always start from loading the program from a fixed memory location. You don't have any flexibility. Okay, so if you have also to make the code what we call a relocatable, okay, you use this notion of relative addressing. Okay, so this adds to the feature of relocability of the designed assembly language program. Okay, so so this is first we will describe this base relative addressing. Okay, So here in base relative, B is set to 1, P is set to 0. Okay, and so the STX length. Okay, so this base, the content of the base register is 0033, and the displacement field is 0. So the effective address is 0033 plus 0. So that is 0033 itself, from where the content is loaded into the index register X. Okay, so this no, sorry, this is STX is indexed addressing. Actually, this is not base relative. So here it will be then. So you have to. So this is OSTX length. So it is stored in the index register X. Okay. The addressing is relative, but the content is stored in the index register X. Okay. So for program counter relative, okay, the field is interpreted as a 12-bit signed integer. Okay. Yeah, in base relative it was unsigned integer. So that's why you see the displacement field is 0, displacement less than or equal to displacement less than or equal to 4095. Okay, so that is 2 to the power 12. Okay, so but here it is signed minus 2048 less than or equal to displacement less than or equal to 2047. Okay, so basically you can jump forward and backward. Okay, move forward and backward by, since you have signed this value in the displacement field. Okay, so the program counter relative addressing, this field is interpreted as 12-bit signed integer with negative values represented in 2's complement notation. Okay, so the effective address is the return address. Okay, so here if you have this STL, stored linkage register return address. Okay, so PC is 0003, displacement is 002D. Okay, so the effective address is adding 0003 with 2D. Okay, 2D is basically this is in hex, right? So A is 10B, C, D. So D is 12. So 12 plus.
So D is 13. So
Right, D is 13, right? 13. So 32 plus 13. So that is 45, right? 45 plus this 3 is added, so 48. So return address is 0030. This is also in hex. So 3 multiplied by 16, that is 48. So that is what is calculated here. Okay. So linkage register contains the content of return address 0030, that is 48 in decimal. Okay. So if bits B and P are both set to 0, okay, so in that case, this the displacement field of the format 3 instruction is said to be taken as the target address. Okay, for a format 4 instruction, both B and P are normally set to 0, and the target address is taken from the address field of the instruction. Okay, we'll call this direct addressing to distinguish it from the relative addressing mode described above. Okay, so you can see that here here you LDL length. Okay, so here length contains the content of length is 0033. So that will be transferred into accumulator. Okay, so so that's that is, and so that's this is so any of the addressing modes can also be combined with indexed addressing mode. Okay, if X bit is set to 0, then it is indexed. As a indexed is there in SIC version also. The term X is added to calculate the target address. Notice that the standard version of the SIC machine uses only direct addressing without indexing. Okay, so with or without indexing. Okay, so you can see this store character buffer X. Okay, so you can see that this so the content of buffer, this is 0036. Okay, is added to this. This will be actually this will be so the displacement field. So this sorry, this X will be here. This will be X. So that is 0033. Displacement is 3. So these two contents are added to get the value 36. Okay. So this so the buffer address, the so accumulator A contains the content of buffer 0036. So the character that is stored in this location will be transferred into the accumulator. Okay. Bits I and N in formats 3 and 4 are used to specify how the target address is used. If I is equal to 1, N is equal to 0, it is immediate addressing. The target address itself is used as the operand. Okay, so the value, operand value, no memory reference is required. This is called immediate addressing. Okay, and if so this is an example, LDA 9. Okay, so in this 12-bit field 9 is stored. Okay, so this content is directly stored into the accumulator. No memory referencing is required. If I is equal to 0, N is equal to 1, the location given by the target address is fetched. Okay, and the value contained in this word is taken as the address of the operand value. Okay, so this is address of address, you can think of actually. So this is you see that, and this is N is equal to 1, I is equal to 0, 0, 0, 2A. In this location, this instruction jump return address. Okay, so this is so program counter is 002D. Displacement is 003. Okay, so as we have seen earlier, this is 45 plus 3 makes it 48. So return address becomes 0030 in hex. Okay, so this content, so jump to the content of the address 0030. Okay, return address. Okay, so this is what is called indirect addressing. Okay, so 0030 contains the address. Okay, so I will illustrate this with an example. Actually, it will be more clear. So if I and N are both 0 or both 1, the target address is taken as the location of the operand. We'll refer to this as simple addressing. Indexing cannot be used with immediate or indirect addressing modes. So now we'll see this SICX instructions that specify neither immediate nor indirect addressing are assembled with bits N and I both set to 1. Assemblers for the standard version of SIC will, however, set the bits in both of these positions to 0. Okay, this is because the 8-bit binary codes for all SIC instructions end in 00. Okay, all SIC machines have a special hardware feature designed to provide upward compatibility mentioned earlier. If N and I are both 0, then bits P, E, and E are considered to be part of the address field of the instruction. Okay, rather than flags indicating the addressing modes. This makes instruction format 3 identical to the format used to the standard version of the SIC machine. This provides the upward compatibility. Okay, so this now we'll see an example. Okay, so that would illustrate this all these addressing modes. So this is an example. Okay, so here if you see, so this here in the first case you have p is equal to 0, p is equal to 1. Okay, so this is program counter relative. Okay, so see the program counter is 3000. Okay, so and the displacement field you can see is uh, um, 0. So this with 3000, 0 is added, gives the same value. Okay, now in 3 location 3000, you have this value. Okay, 3600 actually. So now this this 3600 is in turn, okay, the address. Okay, so this 3600 contains the value 103000. So that is what is transferred into the accumulator, 103000. Okay, so this is the address of the address actually. So this three three this 3000, okay, is the address of the address. Okay, uh, so this is, yeah, program counter relative. So the displacement 3, just a minute, target address is 3600. Okay, so no, displacement address is right. Displacement contains this, it is not 0. This is, you can see that this is 6. Okay, 600. So that's why with this 3000, this 600 is added to give 3600, whose content is this. Okay, so this is the target address, right? So 3600 is the target address from which this content is fetched. Okay, so this content is added with the program counter. This is 600, the content of the displacement field. When p is equal to 1, p is equal to 0, the content of the displacement field is again 6, and this is now added to the base register. The base register content is 600, so 6600. Okay, so 6, no, just a minute. So this is base, and also the index content is added. So this is 6. Sorry, this is not 6. This is, see, this is shifted 1. So this is actually 3. So 300. Okay, and index field is also set. Okay, so base plus this displacement plus index. Okay, so base 6000 plus displacement field is 300 plus 90, so 6390. So the content is this of 6390C300 C303. So that is what is loaded into the accumulator. Okay, now next we have b is equal to 0, p is equal to 1, program counter relative, and you have n is equal to 1. Okay, I is equal to 0. Okay, so in this case, the content of the displacement field is 0, 30. The content of the displacement field is 30. So 30 is added because it's program counter relative. 30 is added to the 3030 is the content of the program counter. which is the address of the address actually now, because it's indirect addressing. Okay, so 3030, when you are storing 3030, the content is 3600. This is this is address of the address. This address from the location from this address is fetched. So 103000. Okay, so this is 103000. Okay, 3030 is the target address, which is the address of the address. Okay, so the content that is loaded into the accumulator is 103000. Okay. Now here you have immediate addressing because I is set to 1. So the content of the displacement field will be directly transferred into the accumulator. Okay, the content of the displacement field is, you can see, is 30. So the accumulator content will be 30 in hex. Okay. Next we have Ni both 0, but P and E set to 1. Okay. Here you have B is equal to 0, P is equal to 1. But n and I, when it is set to 0, okay, it will be treated as program counter relative. So the displacement field is containing 600. Okay, and this is same as the first case. So the content of location 3600, that is 103000, will be stored into the accumulator. Okay, so this is, but this one is a little bit different. This one here, it is n is equal to 1, I is equal to 1, and E is equal to 1. Here it is an extended type of format. Here the address field will be 20-bit long. So this is 1, 2, 3, 4, 5. 5 hex digits. That means 20-bit. Okay. So the target address will be, this is, so this is, you can see that 1 is C. This is 12, right? So this is 12. This is C. This is 3. This is 0. This is 3. So C303. Okay. So the content of this is 003030. 003030. That is what is loaded into the accumulator. This is extended format. This is, you see, usually you see the plus instruction in the front of this assembly language mnemonics. Okay, so you will now we'll see the instruction set. So SICXC provides all the instructions that are available on the standard version. In addition, there are instructions to load and store new registers, LDB, load into the base register, STB, store into the base register to perform floating point operations. It has added some more arithmetic operations like addf, subf, malf, leavef. The addition in floating point, subtraction in floating point, multiplication in floating point, division in floating point. There are also instructions that take care of operands from registers besides RMove, that is register move instructions. These include register arithmetic instructions, ADDRs, add register, subtract, add R, sub R, mal R, du R. Okay, a special supervisor call. Okay, SBC is provided. Executing the instruction generates an interrupt that can be used for communication with the operating system. There are also several new instructions. Okay, for these SICXC versions. And the input output is very similar. The IO instructions we discussed SIC are also available in the SICXC. In addition, there are IO channels that can be used to perform input and output while CPU is executing other instructions. Okay, these allows overlap of computing and IO. Okay, resulting in more efficient system operations. So the instructions SIO, TIO, HIO are used to start, test, and halt the IO channels. Okay, so next we'll see some assembly language programming examples. Okay, on both of these machines. Okay, so the section presents simple examples of SIC and SICXC assembly language programs. These examples are intended to help you to become more familiar with the SIC and SICXC instruction sets and the assembly language. It is assumed that the reader is already familiar with the assembly language of if you are familiar, means it would help actually some microprocessor. Okay, so the primary subject of this book is systems programming, not assembly language programming. Okay, so the chapters contain discussions on various types of system softwares, in some cases simplified instructional computer programs that are used to illustrate the points being made. Okay, so the section contains materials that may help you to understand the examples more easily. Okay, so however, it does not contain any new material on system software and system programming. Okay, so some examples. So this is an example figure. This assembly language program shown in this figure. Okay, contains examples of data movement operations of SIC and SICXC machines. There are no memory-to-memory move instructions, thus all data movements must be done through registers. So this figure shows two examples of data movement. In first, a 3-byte word is moved by loading it into register A and then storing it in register at desired location. Storing the register, this accumulator A, okay, in the desired content of the accumulator. Exactly the same thing could be accomplished using index register X and the instruction LDX STX or LDL STL, that is linkage register. Okay, so in the second example, a single byte of data is moved using instruction LDCH and STCH, load character and stored character. These instructions operate by loading and storing the rightmost 8-bit of the accumulator. Okay, the other bits in the registers are not affected. So this figure shows 4 different ways of defining storage. So how the data area is defined, you should take a look. Okay, because that would help you in designing. You'll be compiling some assembly language code, so that will help you. Not compiling, assembling some assembly language code to the assembler. Okay, so so this is the translation process. So figure 1.2a shows 4 different ways of defining storage for data items in the assembly language. Okay, a statement word. Okay, so there is a statement word, you can see 5 actually. Word reserves 1 word of storage, which is initialized to a value defined in the operand field. Okay, the statement. So this is the statement word in this program actually defines a data word labeled 5. Okay, and the value is initialized to 5. Okay, the statement RESW, so reserved word. Okay, so um, that reserves whatever the number you are putting, it will reserve that many words. So this is a 1-word variable. Otherwise, that will be that many word variable. So alpha is a 1-word because you have put 1 here. So alpha will be a 1-word variable. The statement RESW reserves 1 or more words of storage for use by the program. For example, RESW statement defines 1 word of storage alpha, which will be used to hold the value generated by the program. Similarly, there is byte and reserved byte. You can see in that program there is byte. Okay, that is same as similar to the version of word. Okay, here we are storing character. Okay, so there we are storing an integer. Now we are storing a character. Okay, byte in 1 byte. Okay, so that is stored in CHARZ, CZ. Okay, and reserved byte. Okay, here we have reserved word. You have reserved byte. This is storing 1 byte variable. Okay, so this is used for reserving for 1 byte variable. Okay, you can store multiple bytes or multiple words that will perform an equivalent function of an array. Okay, so the instruction shown in 1.2a also work in SICXC. However, they would not take the advantage of more advanced hardware features. So this 1.2b shows the data movement instruction that might be written SICXC. Okay, so this is see this program um, is see this is I write here I have used this data part to store this file. So it will store in the accumulator the content of this variable 5, that is actually 5. Okay, then it will store this content of the accumulator in the memory location alpha, which is reserved for one word variable. Okay, similarly it will load in accumulator the character z, that is stored in charz. Okay, in the lower order bits. Okay, and then it will store in the content of the accumulator in the memory location, that is a one word reserved byte C1. Okay, it will be transferred there. That Z will be transferred into the location C1. So this is how we wrote the program in SIC machine. But in SICXC, we can make use of much more rich addressing mode. We can use immediate addressing mode. That would make the program a lot more efficient. Okay, that is what is the purpose of assembly language programming. Why we code for assembly language programming? Actually, we want to make the code much more optimized and efficient. Okay, so if you can write the programming high level language and the compiler will translate into machine language, or which has a one-to-one mapping with assembly language. So, but if you though the compiler performs certain optimization, but for special purpose applications, if you write the code on your own in assembly language, you can write a much more optimized code. That is the main purpose of assembly language programming. Okay, so here we are using much more rich instruction set of the SICXC machine, which have the facility of immediate addressing. So load accumulator number 5. So it's stored 5. Then store accumulator alpha. Okay. So this alpha, of course, has to be defined. Okay, as reserved word. Okay. And similarly, load accumulator 90. It is again using immediate addressing mode. Okay, which is the ASCII character code for the character Z. Okay, and then it is storing character C1. This here you have to only use this alpha reserved dot 1, C1 reserved byte 1 in the data area. Okay, so this you can see, yeah, alpha reserved dot 1, one word variable, C1 reserved byte 1, one byte variable. So this is a much more optimized code. Okay, but this is only possible because I have a much more rich instruction set. Okay, so this so that's you can see the so this so the instructions would also work on SICX machine. However, they would not take advantage of much more advanced hardware features. So this next program shows the two data movement options as performed on written on SICXC example. Okay, in this example, the value 5 is loaded into the register A using immediate addressing. The operand field for this instruction contains the flag hash, which signifies immediate addressing, and the data value to be loaded. Similarly, the character Z is placed into the register A by using immediate addressing to load the value 90, the ASCII code for the character Z, which is the decimal value of the ASCII code, which is internally represent the character Z. Okay. Next, we will see another example.
Excuse me, sir.
Yeah.
Sir, some of us actually have a class from 9
Okay,
a.m.
okay, okay.
Can we,
I'm stopping now. I'll continue in the next tutorial. There are some other assembly language programming examples and further topics. Okay. So if you have any questions, you can ask. Okay. And otherwise, I'll conclude the today's tutorial. Okay. So, all right. So if there is no question, I'm